Hello, this video will go through the Physics Higher Tier Paper 1 from May 2018 and question number 6. As ever, press start and stop as the video goes on, working at your own pace. So let's get started. Question 6. Smoke alarms contain an alpha radiation source and a radiation detector. So straight away I'm thinking this question is all about alpha, beta or gamma. So let's remind ourselves, alpha is 4 and 2. So it's a helium nucleus, so we can also write it as this. I can remember that it only travels a short distance in air because it's highly ionizing, and therefore it is not very penetrating. Linked to that, I might need it, I might not, is beta, or also written E and then 0 minus 1 because it's a fast moving electron. And then the final one is gamma, and that has no charge. So this one is the least ionizing or the most penetrating. And then our beta particle, our fast moving electron, is the one that's in the middle. Okay, I've remembered a little bit more about radiation. Let's read on about the question. So figure 9 shows part of the inside of a smoke alarm. So we have a alpha source of radiation, and I can see that it's going from left to right, and smoke particles, they're hot so they rise, and I can see that the alpha particles getting stopped because that one's slightly shorter than the others. So 6.1, the smoke alarm stays off while alpha radiation reaches the detector. So the alpha radiation is reaching the detector at the top at the minute. Why does the alarm switch on when smoke particles enter the plastic casing? Well, that's because we've got the alpha radiation and then the smoke is absorbing the alpha radiation. For question 6.2, why is it safe to use a source of alpha radiation in the house? Well, that links to the idea that it's highly ionizing, as we mentioned earlier, but we also mentioned that it's not very penetrating. In other words, it doesn't travel very far. So if we imagine ourselves in a room, at the top we have the smoke alarm. Now, because it can't travel very far, it might only reach, say, that distance. It is only a couple of centimetres, 2 to 3 centimetres in air. Anyone that's then standing on the floor, then it would not be able to be absorbed into the body just because it's too far away. So why is it safe? It's not very penetrating, it's highly ionizing, therefore does not travel very far. For question 6.3, the smoke alarm would not work with a radiation source that emits beta or gamma radiation. Explain why. Well, at this point, let's just look at the picture. So the reason that alpha radiation works is because it's so easily absorbed by particles. It's so highly ionizing, it's got a high charge of +2, so anything that it hits, it will react with. Whereas beta, we said earlier that it's a fast moving electron, it has a charge of -1. Gamma has no charge, and because it has no charge, it will pass through and penetrate through absolutely anything. It takes really thick lead or thick concrete in order to absorb the radiation. And then beta's in the middle. You need a few millimeters of aluminium. So the smoke alarm would not work with a radiation source that emits beta or gamma because it would pass straight through the smoke. It would not stop. Alpha, with its high charge, would absorb it, whereas beta and gamma would not be absorbed. It would penetrate straight through, and therefore there'd be no change in the count rate to the alarm circuit. The reason the alpha detector works is because when the smoke particles get in the way, that then stops the radiation from getting through. So that then sets the alarm off when it's no longer receiving radiation from the alpha source. Question 6.4. Figure 10 shows how the count rate detected from the radiation source in the smoke alarm changes with time. So what we can see, we've got a nice curve, and the curve decreases rapidly at the start and it starts to level off at the end. And as soon as you see a graph like this about radiation and count rate, then the word to think about, and it's written here, is half-life. So we need to remember what half-life is, and that's the time taken for half of the radioactive nuclei to decay. Let's just read on. So the smoke alarm switches on when the count rate falls to 80 counts per second. Explain why the radiation source inside the smoke alarm should have a long half-life. If it's a long half-life, that means that the count rate won't change very quickly. So if it takes a long time for the radiation to halve, then it's going to stay constant for a lot longer. So the first mark would be that the count rate doesn't change very much if it's got a long half-life. And although it's not obvious what you have to do next, you need to use the graph. And by all means, look forward on the question and you'll see that there's no other question here using the graph. So there's always going to be a reason for giving a graph, and that's a case of using it. So the smoke alarm switches on when the count rate falls to 80 counts per second. So that is just here. So what you can do is you can find out how many half-lives have happened at that point. And if you look closely, that number is at 1.3. So what you can say is after 1.3 half-lives, the smoke alarm will be activated all the time. In other words, after 1.3 half-lives, there will no longer be radiation passing from one side to the other because there's just not enough radiation left. The radiation source has lost the majority of its radiation, so it no longer sends the signal from the left-hand side to the right-hand side, so it will make the alarm sound all the time. So that's why the half-life is made large in smoke alarms, because otherwise you'd have to continually change your smoke alarm, not because it is going off because of smoke, but because the radioactive source has run out of energy. And finally, on to question 6.5. So figure 11 shows a patient who has been injected with a radioactive source for medical diagnosis. Explain the ideal properties of a radioactive source for use in medical diagnosis. So we've just been talking about half-life. Previously, it was a very long half-life, whereas in a person, if you're injecting them, you don't want them to be radioactive for very long. So what you need to do is make the half-life nice and short. You want it to last maybe just a few hours rather than a few 100 years like you might in a smoke alarm. And of course, if you're radioactive for just a short amount of time, there's less chance of damage to cells or tissues or organs within the body. So there's another reason. Another property would be to have a low ionizing power. And if it's less ionizing, then it can do less damage to the cells. So something like alpha is highly ionizing, and if that gets into your lungs, that can lead to all sorts of complications. So you would never use alpha inside the body. It's too ionizing. It will react with anything far too easily. So what you want to use is something that has more highly penetrating properties. In other words, once it's in the body, it can leave again. And that's the sort of thing that you want. So something like gamma radiation, once it's in, it can get out and will do a lot less damage than something that is more ionizing. And of course, if it can leave the body, it can be detected. That brings us to the end of question 6. And as ever, if you have any questions, let me know.